a lot of visual things, I hope. And the background is to this talk. I will talk about the physical background in the talk. The other background is yesterday's talk, which you could regard as background to this talk. So, so here again is the perennial problem, whether something is knotted. And this one also is unknotted. You might try to unknot that in your mind. And then there's the story of having a bracket polynomial around, which I told yesterday, so I won't tell it again. So I'm skipping through this, but we might remember that indeed the bracket is the sum over all these states, and we talked yesterday about how you can think of this as a whole series of surfaces that are interconnecting all of these, and that those surfaces are important for understanding invariants that you can get out of the knots and links, but that's all we need to carry forward from that. So I want to begin by talking about knotted vortices. And this is a picture of a knotted vortex from the work of Kleckner and Irvine around 2012. It's a vortex in water. And this was the first time that anybody produced an actual vortex in a fluid, although Lord Kelvin had suggested that atoms were modeled by vortices in the ether back in the 19th century. And that had begun the study of vortices, but to actually experimentally encounter a vortex or to figure out how to make one, waited until 2012, which is very interesting that it took so long. But you can imagine this, because suppose you were asked how could you blow a knotted smoke ring? You know how to blow a smoke ring. That's a circular vortex. That's a one-dimensional vortex that you're blowing. How would you blow a knotted smoke ring? And that's what these fellows addressed themselves to that question. How would you blow a knotted smoke ring? But instead of blowing smoke in the air, they are making it happen in a fluid, in water. And you can make a ring vortex in water by the same method that you would to make a vortex in the air, only they use a kind of dual method. I'm going to skip Lord Kelvin, we mentioned him. But these are some of, I'm sorry, I'm digressing, but these are some of Kelvin's knots drawings. And he and and it is the case that he and Maxwell and Guthrie Tate, a lot of people worked on knots and vortices in the 19th century, and that was the source of the beginning of knot theory, all of that. I am digressing, but I like this picture. The theory they had was very popular, and so other people, spiritual people, for example, got interested in it. And this is a drawing that was dear to Ledbetter and Besant, who were theosophists, and they felt that the knots represented some kind of intermediation between the world of spirit and the world of matter. And how they came to this particular drawing, I have no idea. It's an interesting knotted drawing. Getting over to Kleckner and Irvine, I was saying that you can make a ring vortex in a fluid not by blowing smoke, but by pulling a template downward along the edge of which the fluid flows and vortexes at the edge. The cross section is a foil like that, and that makes the molecules spin as they go off the edge, and you pull this down quickly through the water, and the ring vortex will float up above it. So they knew that, and they could do that. So how do you make a knotted vortex? Make a knotted template. And that's what they did. They made knotted templates. They used 3D printing to give them a flexible method for trying out different templates. And they converged on a trefoil knotted template that really does give a vortex knot. That was their method. Here's an unknotted vortex happening the way I described to you. The template was pulled down quickly through the water, and then high-speed photography is showing you the vortex. Just there, sorry. That's the knotted vortex happening. And the high-speed photography now is very useful because this thing doesn't last very long, and you get to see different shots of it and convince yourself that you really have a trefoil knot there. I think it's interesting enough to see twice. So here's the template itself, and then you can watch it being pulled down quickly. And the vortex coming up. Definitely a trefoil knot. These are some shots from that. You can see that when it pulled down quickly, there's a lot of action right near the edge, but it's the forward edge that has enough stability to last a little while, and all that stuff in between is very volatile and it goes away quickly. So that after a little while, all you see is the forward edge. And the forward edge isn't lasting very long either. I don't have the figures on how long how much time is passing. Sorry. If we look in the paper, they may tell us. But it doesn't last long, and it tends to fall apart. I don't have a direct picture of it falling apart here, but the way it falls apart, this is a direct picture, but not from that movie. It falls apart by the vortex comes near itself and interacts with itself, goes through some hard to describe stuff, and ends up re-smoothing itself in the other direction. Reconnection, it's called. So a reconnection occurs between this and that, and the reconnection is from the point of view of a topologist, a re-smoothing of this. This is, you think of this as smooth one way, and now you've smoothed it the other way. Something interesting happens in between. So this tends to happen again and again in the knotted vortex, and it just falls apart into an unknotted collection of circles as a result. And this leads to a nice question, which is how many reconnections do you need in order to get rid of a knot, in order to unknot a knot or a link? How many reconnections do you really need? Maybe you only need one, maybe you need 100. Depends on the knot or the link. And how many are happening in these situations? So another method other than water is to use a differential equation and evolve a vortex using the differential equation. And these fellows happen to be very good at doing models using a nonlinear Schrodinger equation, the Vortices equation. And then the vortices are phase singularities in the evolution of that differential equation. And one can then make some computer studies of what happens there. So you have a nonlinear Schrodinger equation like this. The solutions of the Schrodinger equation look like this. There's a phase, and the knot is places where the phase is not determined. And one can then watch how that behaves and make movies of it. Here's a movie that they made of the trefoil simultaneously doing 3 reconnections and ending up unknotted. like that. Of course, if you went backwards, you could do some dreaming, because you could imagine that you had something that was unknotted and it went through a reconnection and ended up knotted. So I think that's an interesting dream, but it's obviously less stable to, not so obvious how you would, arrange that to happen. So it tends to fall in the other direction. In this situation, anyway, that these tend to fall apart. Now, how can we model this? Well, you think about how the vortex works. The fluid is going around the line. And the fluid, and if I say the fluid is going around the line, then I can make up a notation for that, because I can take the right-hand rule and orient the line in such a way that the orientation of the line tells me the direction of circulation around the line. Okay, use the right-hand rule. But then if the line is going downward, you see the circulation goes this way. But then you see that if they come together that way, then this circulation and this circulation can add up in the space between the two lines. And it's under those conditions that the reconnection can happen. All right. If they come together and one is trying to flow this way and the other is trying to flow that way, then they just kind of repel. So under these circumstances, oppositely oriented lines, you can have a reconnection happen. And then if you're looking at a knot diagram and thinking, well, where could it reconnect? You see, oh, at a crossing, for example, there's an outgoing line here and an ingoing line here, and you could have a reconnection happen right there. Could, conceivably. And then you can start playing around with different possibilities of reconnection on the diagram. And it is oriented reconnection that we're talking about. So I can't do every resmoothing that I would like. When I'm doing the bracket polynomial calculations, I do every possible resmoothing that I don't care. I don't care about the orientation. So the bracket calculation is not going to immediately tell me information about the reconnection. But curiously enough, by going through some longer story, like the one I told you yesterday about using covanophonology, you do get information about reconnection, as we'll see. So we have this a simple-minded combinatorial way of thinking here, of taking a knot diagram and imagining how to reconnect it to make it unknotted. So for example, I have a trefoil here, and I reconnect here. I go through a saddle point, and I end up here. And now I have a hop link. And the hop link has to get unlinked, so I need another reconnection. So I do it here, and I end up with an unknotted curve. So two reconnections will undo a trefoil now. I don't think I've said anything on the slide that I didn't just say. Here's another experimental one. This is the knot 6-2, and it's going to undergo a little evolution here. And you see, it turned into a link. Then it turned into a trefoil knot, and then there were two more reconnections. And those are the ones that we were just talking about. How did it turn into a link? Well, you have to look a little closely to see how it turned into a link. Let's see if we have a picture of it here. This is the original knot 6-2, and then a reconnection occurred here, and it turned into the link. And then the link went on and turned and got down to unknotted by turning into a trefoil knot, and that happened somewhere else. I won't worry about it. So let's think about this. We can think about the world line of what's going on, and when a reconnection happens, then you can, if you want to think about the world line of it, then there's this period when it's this way, and then it goes through a saddle point in our theoretical picture. Of course, it goes through something more complicated than a saddle point in reality, but a saddle point will fill in a nice smooth bit of surface that starts us here and ends us at the reconnection. So instead of the physical reality, I'm putting in a world line that looks like a saddle point smooth surface between one part and the other. And then along with that, you can think of other smooth surfaces that you might want to put in place here. You could have a circle that would die out if you wanted to build surfaces going on in the fourth dimension. So I'm thinking of times going this way. It says times going this way. So this evolved that way. And this was the birth of a circle. And this was the death of a circle. And here, a circle gave birth to two circles by going through a saddle point. And here, two circles gave combined to give you one. Here, nothing happened. Here's a different kind of evolution. A circle, and then a circle was born. And then these two circles went through a saddle point, and then we ended up back with a circle. It might be knots. We're just talking about it in the abstract. And some genus could occur because you might have a circle that gave birth to two circles and then went through a saddle point and ended up back over here. And you created a surface with some genus in the temporality of that process. Now, for our purposes, we're not necessarily thinking about this because we're only thinking about reconnection. So reconnection corresponds to saddle points, but when I think about this kind of thing more generally as a topologist, then I'm thinking about births and deaths of circles because I'm thinking about what kind of surface could go between one knot and another and in four space. And the surface might have births and deaths in it and other things. And what I'm asking topologically is what's the least genus that could span between one knot and another? Here's a knot in three space. Here's a knot in three space. Here's four space in between. What kind of surface can I make? What's the least genus that I can make? And if I ask that question, then within that question is the question, what's the least number of reconnections that will happen? Those being the count of the saddle points that occurred in there. So we can think about it in this context of world lines, four-dimensional, and surfaces embedded in four dimensions like that. So then I'll return to 6.2 in a moment, but then our picture of what happened with the Teflon knot can be put in a four-dimensional frame as well. You started with times going down the page now. You started with the Teflon knot and you went through this saddle point and you ended up with two circles, and then you went through another saddle point and you ended up with one circle, and the Hopf link happened in the middle. Well, in the schema that is showing us the surface, you see, here's the Teflon knot, and here's the Hopf link, the two components of it, where you went through a saddle and you ended up with two components. And then these two components together went through a saddle with each other, and you ended up back at one component, and you had a bit of genus as a result in the surface in four space. And we had two reconnections. So these two reconnections look like the two ends of this hole. And one bit of genus occurred for two reconnections. And so we can count genus and think of it as related to two reconnections. And if I knew that a surface had a given least genus in four space, then I wouldn't be able to get from one to the other in less than 2G reconnections, because I would have to go through 2G saddle points in order to get from one to the other. So we can think that way about the problem. Here's 6.2 again. And this is what happened. It turned into a link. And then up here, that's that two component link, and then it went through another saddle point over here and turned into the trefoil knot. And then the trefoil knot went away. So it took 4 reconnections in that experiment to get rid of 6-2. But the funny thing about 6-2 is that it's very close to being unknotted. If you look at this crossing and switch it in your mind, you'll see that it's unknotted. And if it requires a little more seeing than that, I think I have a picture of it here. I switched this crossing. Now you just push that over a little bit and pull that back under and it's unknotted. So 6-2 is very close to being unknotted by switching one crossing. What does switching a crossing have to do with reconnection? Well, maybe not a lot in a physical situation, it would depend, but in a topological situation, it's related. If I want to switch a crossing, I can accomplish it using 2 reconnections. Fine, let's see that it's true. So I start with this crossing here, and I put a little twist in there so that I have this line going backward. This one's going forward, and I'm allowed to do a reconnection there. So I do it. Now this is going underneath, so I pull it back, and then I push it back over the top, isotopy, and then these two are going in opposite directions, so I do saddle, and there I am. I switched the crossing. This curl got changed a little bit from being twisted one way to being twisted the other way, but who cares? So I just get rid of it. So topologically, I start here, put in a curl, go through 2 saddles, get rid of the curl, and I end up here. So I can do a switching of a crossing using 2 reconnections in principle. Now, whether that would occur in some physical situation or quasi-physical situation like the Vortices equation, I don't know. It would be interesting to see it happen. But in principle, that says that 6-2 can be undone in 2 reconnections. So its reconnection number is not 4, it might be 2. Reconnection number being the least number of reconnections needed to undo it. So we could do a little science fiction here. Here's 6-2. It happens to have a curl conveniently placed, and it went through the saddle point, and then this part slid from over to under, and then it went through the saddle point again and ended up being unknotted. Does that ever occur in some field theoretic physical situation? It'd be nice to see if it did. I think I just said what's on this slide. So we'd like some lower bounds for the number of connections, reconnections that you would need. And here's a nice lower bound. There's a classical invariant of knots and links called the signature of the knot. I'll explain what it is in a moment. This is one that you can actually do some computations with yourself if you want. You really can. The signature of the trefoil is -2, and the signature of 6-2 is also -2. And the absolute value of the signature turns out to be a lower bound for the reconnection number. That's the theorem. Signature, absolute value of the signature is less than or equal to the reconnection number for the knot. And the reason is that twice the 4-ball genus is less than or equal to the reconnection number, as I just said. Every time you get a bit of genus, you get 2 saddle points. And so the least number of saddle points that you're going to need is given by the genus. And so that has to sit below the reconnection number, which is counting saddle points. Okay. And then here's a fact from classical knot theory due to Murasugi, that the signature, absolute value of the signature of the knot is less than or equal to twice the 4-ball genus. So I'll put those 2 together, and you have that the signature is a lower bound for the reconnection number. Okay, what's the signature? Well, what you do to get the signature is you find a surface whose boundary is the knot. I've drawn a convenient surface here, but you may wonder what knot it is, so I'll show you in a moment. The slide says it's the trefoil knot, but why should you believe that unless you did the exercise? But it's some knot. And on this surface, which I've presented in a way that I can look at and think about, there are two basic curves. This one going around that handle and this one going around the other handle. The surface retracts onto those two curves, which is two circles touching at a point. So the topology of the surface is held by those two curves. And then, so there are a canonical set of curves for the surface. And then you look at the linking numbers between these curves. Well, not quite, because they intersect. But what you do is you define a linking pairing by taking one curve and pushing it in the direction of the positive normal to the surface and looking at its linking number with the other curve for two curves. So if you took B and you pushed it in the direction of the positive normal this way out of the screen, then it would be floating above A, and so there'd be zero linking number. So that says that theta of BA will be zero, but theta of AB, if you push A up the positive normal a little bit, then you see that A is linking B, and so you get a linking number there, and so theta of AB is 1. And then the self-linking, in order to see the self-linking, you have to push the curve off the surface a little bit. And then this is a nice exercise for you if you want to think about it. How do you think about this? You push the curve off the surface and think of creating a little band as you do it, right? And it's just like the band you're looking at, except it's perpendicular to that band if you pushed it off the surface in this direction. So the geometry of the way the curve and its push-off look is actually just like the geometry of the way the edges of the band look if you were to rotate everybody by 90 degrees. I don't expect you to believe me, but you can take that as a hint for thinking about how to get at the self-linking number part. And the self-linking number part then turns out to be just calculable in terms of the way this crossing works when those two cross one another. And this gives you you can see that the crossing there is going to give you a -1 in orientation. And that's the linking number between this curve and itself. And so you end up with these numbers here. And it's out of those numbers that one computes the signature. And the way you compute the signature is that you symmetrize this matrix by taking it plus its transpose. And then you take the signature of that matrix, which for our purposes could be just described as the number of positive eigenvalues minus the number of negative eigenvalues of the matrix. So this is something that you can calculate if you want to do a little work from a knot. You find a good surface for it, you find the basic curves in it, you look at the linking numbers, and out of that you can get the signature, and that ends up being a lower bound on the reconnection number. Now, some puzzles that we arrived at in the course of that last slide. Here's the trefoil knot, and here's the surface whose boundary is the trefoil knot. Now I'm pushing the surface around a little bit. See, I pushed it in there, and then I made that a little better. And you see this band, when I pushed it through itself here, I got a little twisted band going from here to here, and I got another little twisted band going underneath from there to there. So I get these two twisted bands going over each other like this. Each one has a 360-degree twist in it. And the outer part is a disc. I just didn't show you the rest of the disc. You can think of it as coming up over the top, if you like. And then I relaxed each of the twisted bands to let them become curls. And then I turned it inside out, and there it is. And that's the surface that I was just talking about. So this is a surface whose boundary is the trefoil knot. Let's see. Here's the matrix. Here's the symmetrization of the matrix. Its determinant is 3. Its characteristic polynomial is this, and I find that it has 2 eigenvalues of the same sign, so the signature is -2. So among other things, that tells us that this knot is inequivalent to its mirror image, because signature will change sign under mirror imaging. It tells us that the four-ball genus of the trefoil is equal to 1 because the genus that we saw here, this genus, but this is a different surface, was 1. So if it's really bounded below by the genus is bounded below by 1, not 2, right, from Murasugi. So must be 1, and the reconnection number is 2. So we've gotten all that out of this little matrix of linking numbers. Another example, here's the figure-8 knot. Now, the figure-8 knot has a surface that looks very similar to the trefoil surface, except this twist is the opposite of this twist. And when you get the Seifert's matrix, you find that you get a -2 and a 2 rather than 2 -2s, and you get a plus root and a minus root, so the signature is 0. So signature isn't telling us anything. And this is typical of this kind of problem. I'm interested in what's the least genus in the four-ball that will bound something, which will give us some information about reconnection number. Well, in this case, the signature didn't tell us a thing, but on another invariant called the ARF invariant does tell us that, that this is not bounding a disk in the four-ball, and therefore it must have genus 1. And therefore the reconnection number for the figure-8 knot is also 2. So you know, you have to reach in general, if you're looking at various knots and links and wondering about their reconnection numbers, you have to reach into your bag of techniques, whatever they are, and see what you can do. Now, the ARF invariant is an amusing one, and I thought I would tell you about that for a moment. The ARF invariant can be described this way. This isn't its original definition. You're going to take link diagrams and knot diagrams, particularly knot diagrams, and you're going to allow this extra move. You'll have two oppositely oriented lines going over two oppositely oriented lines, and you'll have to switch them. So I call that passing bands, because I think of this as a band. It could be filled in with a band, like these bands. And you pass bands, you're allowed to pass bands. And then you find that every knot is pass equivalent to either the trefoil knot or the unknot. So this is an interesting equivalence relation on knots. Once you put that extra equivalence relation on it, every knot falls into either the trefoil knot or the unknot. And the trefoil knot and the unknot are not equivalent to one another. And furthermore, if a knot falls into the trefoil class, it can't be bounding a disk in the four-ball. That's a fact. So we see that just by construction of those surfaces, that the figure-8 knot and the trefoil knot are pass equivalent to one another. So therefore the ARF invariant of the figure-8 knot is 1, and therefore its reconnection number is equal to 2. So we get it that way. And that's an example of, you know, looking for another technique to get at a problem. A related collection of knots is these, where you have end curls here and one here. That's the opposite one. So this, if you had one curl, you'd have the figure-8 knot. If you have two curls, you'd have somebody else, and so on. And you could consider end curls. It's a famous example because it turned out to be very hard to tell whether they were slice or not. And Casson and Gordon, long ago, around 1980 or earlier, showed that none of these are slice knots. And that means they all have reconnection number 2. But here, you really have to use some subtle things about signatures of branch coverings and things in order to get at it. So you might have to reach deep into your bag of tricks in order to get at reconnection numbers if you're interested in arbitrary knots. Now, getting back to surfaces that span knots, there's a general method for finding a surface's boundary is a knot, due to Seifert. Very beautiful idea. What Seifert did was he said, first, smooth all the crossings in an oriented way, and you get a well-defined collection of oriented circles. Then bound each one of these circles with a disk. Sometimes you will have to nest the disks, maybe think of disks that go out into space like this. forming domes, if you like, because they're really nested circles in general. And then connect the circles together with little twisted bands at the crossings that you smooth. And you end up with a surface, and it's orientable, and the boundary of that surface is your original knot. So this is a good surface to have around. It isn't necessarily the least genus surface in a 4-ball, but it is a surface that is sometimes the least genus surface in the 3-ball and in the 3-sphere, and it's available, so you can start there and look for other surfaces you want. And you can, of course, in principle, you can calculate the signature of your knot by forming the Seifert surface and then looking carefully at the curves on the Seifert surface and finding out their linking numbers. You really can. You can write down the surface and then write an algorithm to get all the linking numbers if you want to do it that way. So here's a further observation for our purposes. Suppose that you had the trephine knot you're looking at, and you went through our reconnection, doing reconnections at every crossing on 2 ingoing, outgoing lines. Well, you just got the pattern of the Seifert circles, didn't you? See that? Except that every circle, or some of the circles, have little curls on them because the crossings are still hanging around. But if you were to eliminate those curls, it would just be the Seifert circles. Because what you did when you went through the saddle point here is you created an oriented smoothing with the crossings still hanging around. So Seifert circles and this sequence of reconnections are related to one another. And that tells you that one way to undo a knot would be to do exactly number of crossings reconnections to get the Seifert circles. But you could do better than that, as we'll see in a moment. So what is the genus of the Seifert surface? Well, I just tell you the answer in this case. The genus of the Seifert surface turns out to be equal to 1/2 of the number of crossings minus the number of Seifert circles plus 1. We're going to see some geometry topology about that number anyway, and I just wanted to tell you from the beginning that that happens to be the genus. So twice the genus is the number of crossings minus the number of Seifert circles plus 1. And one way to see that is to use Euler's formula, which says vertices minus edges plus faces is 2 minus 2g. But I'm not going to derive it for you. It's just the number c minus s plus 1 that is going to keep coming up for us. So here it is. This is a nice theorem, which goes by way of Rasmussen's invariant that we talked about yesterday. If you have a positive link, then the 4-ball genus of that link is equal to the Seifert genus for any positive diagram of K. That's the consequence of Rasmussen's invariant that we mentioned quickly near the end last time. So that means, if you believe that theorem, that the reconnection number of K must be greater than or equal to the 4-ball twice the 4-ball genus, must be greater than or equal to c minus s plus 1. Well, we're going to claim that it's actually equal to c minus s plus 1 by constructing a reconnection that does exactly that many times, okay? So we're using a big gun that just gets us directly to this answer. So I'm claiming that if I have a positive knot or link, then the reconnection number is exactly equal to c minus s plus 1. Positive means all the crossings are positive. It means that when you draw them, they all satisfy the right-hand rule, that if you put your fingers in the direction of the overcrossing line, then your thumb points in the direction of the undercrossing line. So that's one possible choice for all the crossings. So how are we going to see this? We need to figure out a way to reconnect it to an unlink or an unknot in exactly this many moves. Well, here's the deal. here's some positive knot. Okay, and I could go along and reconnect at every single crossing, right? If I do that, that's the same as I said before as making up the Seifert circles. Here I've just drawn the Seifert circles. So I didn't draw the little curls, but this would be the result if I did a reconnection at every single crossing. But then you realize, well, I didn't have to go that far. I could have kept these along, I could have kept this crossing just the way it was, and it would just have a little curling with that one. You see, this was gone maybe, and this one is just a little curl over with that one. And this one could be a little curling attached to this one, and this could be a little curling attached to this one, and this is just a curly thing attached to this, but it's all unknotted. And then one last one over here, and I would have all this curly stuff hanging on down, but the whole thing would be unknotted. Here's a picture of it. So I decided I would leave this alone, and this alone, and this alone, and that alone. But I did all the others. So I smoothed it here, and I smoothed it there, and over here, and over here, and over here. And now you see that there's that big curly thing. And then a larger curly thing hanging off here. Well, it's a tree-like arrangement, right? And the way I'm constructing it, thinking of it going down to the bottom, it's quite clear I'm making something that's unknotted all the way up. As long as I don't, in making that tree, make a tree. As long as I make a tree, as long as I don't make a graph of connections that has a loop in it, then I will be creating an unknot. So that means that I can use how many, I cannot use how many crossings? Well, I'm counting Seifert circles, one for this circle, one for this one, one for this one, one for this one, and I don't have to count the last one, right? So I'm going to connect up all the Seifert circles, one crossing between each one to the next one, and I don't have to use the last one, so that's number of Seifert circles minus one. So that means that I need the number of reconnections that I need to make is number of crossings minus number of Seifert circles plus one. There's that number that we were talking about. So that's 6 in this case. And here I'm demonstrating that 6 reconnections will turn this into an unknot. So I can always do this. It didn't have to be positive in order to do that. I can always reconnect some diagram that I have with that. So I can always reconnect with 1/2 the genus of the Seifert surface, in other words. But then in this Rasmussen case, in the case of positives, that is the lower bound. And so I'm done. I know the reconnection number for this. It is 6 by Rasmussen. And so that's the way this works. And that's interesting. It means that we know the reconnection numbers for lots of things. Like here's a positive link. And I might go ahead and figure out that the reconnection number is 2, but then I might make a mistake as I go down through easily, or physically it might happen. So for example, suppose it reconnected this way and became 2 hot links, and then they each need 1. And so I would have gotten into 3 instead of 2. Where's the 2? Well, the method I was showing you says reconnect here and reconnect here. And that will be good enough. And then there will be 2. So you can find where the 2 is by using the algorithm I just told you. But it might be not the one that a physical system would do. I'm still wondering about that. I think we need to go back and do more experiments with the differential equation to find out about that. Here's another class of knots that are positive, torus knots. And in the case of a torus knot, which goes p times around the torus one way and q times around the torus the other way, called type PQ, the number of crossings, if I represent it this way, is q minus 1 times p. And the number of Seifert circles is q. So q is 3. You see, I just moved it that way. And p is the other number. And the C minus S plus 1 is QP minus P, that's the number of crossings. minus the number of ciphered circles, which is Q, plus 1. And if your algebra holds, you'll find that that's equal to P minus 1 times Q minus 1. So that's the result, that the reconnection number for a torus knot is P minus 1 times Q minus 1. And the genus of the four-ball genus of the torus knot is 1/2 of that. And that was what I mentioned to you yesterday using Rasmussen. Rasmussen proves Milner's conjecture that that's the four-ball genus. So we're in that region. By the way, Milner conjectured that in his beautiful book, Singularity of Complex Hypersurfaces, Singular Points of Complex Hypersurfaces. And it was proved by Kronheimer and Moravka by using field theory and analysis. So when Rasmussen proved it using Kovanov, it was the first time it was given a strictly combinatorial topology proof. So that was a very beautiful and hard to get at conjecture for a long time until people had the right insights. But from our point of view, it's very pretty to see how that reconnection number is related to all of that, and how we do know now what the reconnection numbers of torus knots are. So if you did some experiments involving torus knots and found that they're reconnecting with more than that, it would be interesting to see how much more and what the discrepancies would be, and so on. What else do I have here? Oh, right. I could take a relative of 6,2 here that's positive. Here's 6,2. And I switched these two crossings at the bottom, and now it's positive. And now we know that this has reconnection number 4 instead of 2. And you can imagine putting this one into that same experiment, and I bet it would do it in 4. What else do we have? Some lore. Here's a general fact, that if you have a knot and you add it to its mirror image in this way, then it will be sliced. Then it will bound a disk in the four-ball. Any knot connected some with its mirror image bounds a disk in the four-ball. And one way to think about that is that there are saddle points that you can go through that will undo it because of the mirror imaging. See, like here, and you go through that saddle, and in this case, it's all undone. One saddle, and this just comes apart. So, so you see that the reconnection number for this knot plus its mirror image is equal to 1. Needed at least 1, and there it is, 1 for a slice knot, that slice knot. The way it gets sliced, you can have some fun looking at different ways of thinking about the four-dimensional surface. One way is to, of course, amalgamate the whole thing into one surface that's immersed in 3 space, which I've indicated here. We went through the saddle point, then these moved out and bounded disks and disappeared. But another way is to think about how this mirror imaging worked and put lines from one point to the mirror image point and make a surface. And as you do make those lines, then you will find that the surface will intersect itself along some of the lines. And you will get a little kind of roll like that, thin roll that intersects itself. And there's the slice disk. You see what I've described for you as you made those lines, as you went along the knot and its mirror image all the way around, is you made a disk that was immersed in 3-dimensional space that self-intersected itself. The self-intersections aren't in 4 space, they're in 3 space. And when you push that into 4 space, the self-intersections disappear and you're seeing the disk that the knot connected some of its mirror image bounded. So this is some of the lore that we like to think about in relation to the question of whether or not it's sliced. People study cascades of reconnections, and what I've said asks for some look again at those cascades. Other knots occur. For example, in Ivan Smolyak's work and other people, there are knots that occur in liquid crystals and environments like that, and these don't disappear. They're much more stable than the vortex knots that we were talking about. But you can still ask the same question of one of these in that situation. What's its reconnection number and what kind of events are happening with it? So this is just some playing around with some diagram that occurs in thinking about that. What is the reconnection number of this or this? And if it's positive, for example, then you can do a calculation and find it. And you can always estimate reconnection numbers by the C minus S plus 1 formula. And some of these other techniques could be useful. So if you're interested in what is the reconnection number of something, then this should be an encouragement to look at some of these things. Now, at this point in the slideshow, if I were going from the beginning of this slideshow to this point, I would have started telling you what I told you last time, but we have a few more minutes. But of course, I'm not going to do that, but said all that. So I'm jumping to an experiment, a film of an experiment that was shown to me by Renzo Rico, and I eventually met Alex Yanko when we were visiting Novosibirsk. And he started studying vortices because he was asked by a company that manufactured turbines to help them understand the stability of the results that were going on in the turbines. And if you have a turbine, then you will be creating vortices like the water going down your drain. And so Alexienko has experimental setups where he has a turbine going and a big tube, which is wider at the bottom than it is at the top, and there's a vortex being generated down through that. And you're going to see a movie in a moment where this happens, that the vortex has a loop in it, and the loop rises up the funnel and comes underneath itself. And now these are possible reconnection because they're going in the opposite directions from one another. And they could or even here, I was here. And if a reconnection happened, you would get a link. So this goes backward and actually creates some non-trivial topology. It really happens. Here's the film. It goes by too fast. There it is. That's it happening. So the link dropped down. Did you see it? You could try it one more time. Watch. Oh, I have some stills. See, it went underneath. Now it's coming up. And it's getting very nearby here. Nearer. Nearer. And there might be a movie that's better than this where the interactions would show, but not this movie. The next frame is reconnected, and then there's the link. So that's what happened. And you could fantasize about that. like this. I mean, suppose that you had a situation with three of these, and you had two of them go, and you would get a link. And then if you had another one and it could go, then you get a trefoil knot. So it's conceivable that you would get trefoil knot in vortices in that experimental situation. It would be very interesting to see that. With a couple of minutes left, I think I have another visual. I wanted to find another Alexienko visual. If you'll bear with me, we'll see if I can find it. Let's see if this. That's not bad. The point I wanted to make about this is back over here, where this comes near and undergoes reconnection. But watch, see, it's really quite beautiful and complicated, and there are filaments that are going back and forth between the parts that are where it is condensed and become the two parts. So it whets your appetite for seeing whether you could model what's going on there in terms of some texture of interactions that are sort of like Feynman diagrams going between these two. I don't know what the literature looks like in terms of modeling this, so maybe some of you know. I think there might be another one. Now ask yourself here, is that going to be a reconnection? The arrow goes this way, and it comes back around and the arrow goes this way, so no. So these filaments are happening between two parts that can't reconnect because one wants to flow one way and the other wants to flow the other way, but the filaments are there. There is some intense interaction going on between them as they get near one another. And then they just pass by. So I'm curious how one could model that. And I'll stop there.